So this is video 3 in multi-part videos on kinetics. You can find the rest of the videos on my YouTube channel. And today what we're really going to focus on is something called the integrated rate law. So in order to understand that, let's just start with this simple reaction. AB is decomposing into components A and B. So let's say we start with some concentration, say like 0.5 molar of AB. And we're basically going to start decomposing it, and what we're interested with, once again, this is kinetics, so we're interested in time. And the objective is how long does it take to get it down to a concentration of 0.25 molar. And we're going to hold the rate constant at 0.007. Now at this time I'm not going to put units on the rate constant, and you'll see why as we go along in this demonstration. So this is a zero order rate reaction. So what that means is the rate at which this occurs does not matter at the concentration of this reactant that you're adding. So in other words, it's going to break apart no matter how much of that is present. It's driven by something else. Temperature, we know, is one of the factors. But in this case, concentration doesn't figure in. So this is a hypothetical situation, but I just want to show you, if you graphed a zero order equation, the material that's going away didn't affect the rate, then it would go away at a set rate based on that constant K. And so if we graph this, and so in this case we have a 0.007 K, that would be mole per second, or the units on that. Then if you started at 0.5 molar, as time went on it would linearly decay till we got to that point, the 0.25 molar mark, and that would occur in about 35 seconds. So just to understand how different order reactions affect rate, let's go to the same reaction, second scenario, but let's say it's a first order reaction. Now in this case, the concentration of AB does affect the rate according to this rate law expression. And we talked about setting up these rate law expressions in the last video. So now if you graph that, and I'm going to keep the zero order on there just for reference. If you graph that, now once again remember, if the concentration affects the rate, as the reaction goes on this decomposes, so there's less of this as the reaction continues, so the rate drops off as you go through the reaction and it slows down over time. Still decomposing, just decomposing slower and slower each time. So after about 95 seconds on this graph, if you had the same rate constant, in this case now the units is per second, but if you hold that same rate constant and you start at the same 0.5 molarity, then it's going to start decomposing, and you'll get to about 0.25 molar concentration in about 95 seconds. Okay, so here's the third scenario. Now let's say that it's actually a second order rate constant. In other words, it not only depends on this concentration, it depends on this to the second order. So in other words, there must be something going on. We talked about this in the last video, that really there can be fundamental steps that give rise to this overall equation that would explain why this is actually second order in regards to the reactant. And so I just throw that out here. Here's just it's a hypothetical situation, but here's maybe what happens. Let's just say that it takes two of these ABs to actually form this AA complex. So that's somehow, say, covalently bound A to A, and the BB complex. These particular materials then go ahead and decompose, and they do that very fast. So once again, the slow step in a multi-step reaction is what determines the overall rate law. So now if you stacked up these equations and you canceled out everything that's common on both sides, and then you reduce the coefficients, you would have this overall reaction expression that looks like this. But that isn't what determines the rate law. Only this piece determines the rate law. And according to this, that's second order. Okay, so back to the original project here. So let's graph that. If you set everything the same, where you start at 0.5 molar, you do a decomposition, and the constant for that is 0.007. Okay, in this case it's going to be 0.007 per second per molar. But once again, now you starts off very fast, but then it decreases its rate rapidly in a decomposition reaction. So here's some of the take-homes from this particular example. And this isn't really relevant because if you were going through different reactions that have different orders, their Ks are probably different. But I just wanted to hold these the same just so you can compare what happens, how it looks mathematically. But anyway, in this particular reaction, you get to 0.25 molar solution. It would just take 265 seconds. So one of your take-homes is, any order above 0 needs an integrated rate law to solve. In other words, this zero order equation, we could solve it. It's linear. We could figure out the concentration at a set amount of time. Now, we could graph all these and solve that graphically, and that's always an option. But mathematically, if you have a linear expression, it's very easy to solve. There's a function for this, y equals mx plus b, and you can solve for the concentration at some given time. But if I want to solve for these, there's a calculus method that will basically allow us to integrate these, and then we can solve for the concentration at any time along the curve. The second thing is, as order increases, the effect on rate is more dramatic. It doesn't always mean it goes down, it just means it's more dramatic. I held the K constant for each of these three examples. Second order isn't necessarily slower than lower orders, because rate is a function of both K and order together, the constant and the order above the concentration together, and you usually do the rate expression in terms of the reactants. Alright, so this is where we get to this idea of the integrated rate law. Now, I'm not going to do a derivative right now, but I'm going to just send you some references where you can, if you go back to YouTube and enter integrated rate law first order reaction, there's a guy named Chemist Nate. He does a great job explaining this and walking you through. If you've had calculus, I recommend that you do this. This is an excellent exercise to remind you. If you're a student here at Community College Denver, then on D2L I also put some rate law proofs and explanations on D2L that you can look at. Once you get that, if you integrate the rate law using calculus, you can, as I said, find the concentration at any time, T, as long as you're given the K and the original concentration. So you can imagine this is very powerful. If you're in the lab, you know the rate law for some sort of reaction. You could figure out how long you need to run a reaction to get to a set amount of product, or to use up a set amount of reactant. If it's a zero order rate equation, so I'm just reminding you from the other videos what that means, the change in A per unit time, and once again we put a negative on it because we're expressing this in terms of reactants, so reactants are going away. If it's zero order, you basically would take the K by itself. You don't need the concentration of this reactant. We put the zero in there sometimes just to remind you of that, but anything raised to the 0 power is 1. So now if we set up this expression, you can get a linear expression. And if you look at this expression, when you rearrange it, basically what I did is I just rearranged this a little bit. You can find that concentration at any time, if you know the rate constant, times the time you're running to run the reaction, plus the original concentration. Now we go to a first order rate equation. Basically, same kind of deal. We're trying to get down to a rate, but the rate expression is K times the concentration raised to the first power. And if you did the calculus on that, you'd end up with this expression. The A at any time, start with the original concentration, use your mathematical function E, raise it minus KT, power of E, and you can solve at any time for the final concentration. Second order rate equation, as we know here, you're basically raising this to the second power. If you do the calculus on that and integrate, you'll end up with this expression which says, look, you can find the AT at any time if you know the original concentrations, the K, and the time. You should memorize these integrated rate equations, and now let me give you an example of how you can use them. The decomposition of sulfuryl chloride at 373 K has the following rate expression. So if we started with 0.5 molar sulfuryl chloride, and it's in nitrogen gas, and notice it's in a 1 liter container, so that makes things simple. 0.15 moles are in that liter, and that makes it a 0.15 molar solution. What concentration of this material would be present after 25 minutes if you know the rate of decomposition? And then what's the concentration of chlorine you form at that time? Let's just say you're running this to create chlorine gas to purify water or something like that. Well, first off, let's determine the order of the reaction. And we're just doing simple one reagent reactions to get you introduced to this today. And you look that this is raised to the first power, so that's a first order reaction. So now we just apply the appropriate equation. The one caution I'd say is pay attention to the units. All right, so we're given 25 minutes, but look at the rate constant. It's in what units? Seconds. So that is a mismatch, so we need to do a conversion, and it makes the best sense to convert the time out back to seconds so it'll match with the rate constant. So that's fairly easy, 60 seconds per minute. You're basically working with 1500 seconds. Answer is, it's 0.12 molar after it's ran for 1500 seconds. So now the next question is, what's the concentration of chlorine at that time? So let's think about this. The nice thing is we're running in a 1 liter container, so the molar changes are also going to be equivalent to the molarity changes. So if I'm at a 0.15 molar solution, I end up at 0.12. Well, I must have just used up the difference, which is 0.03 molar, right? Well, the amount that I used up is 1-to-1 with how much of this and this is formed. So it's basically 0.03 molar chloride gas solution formed as well. So that's one of the ways that you can use this. If you integrate the rate law with calculus, and you can also get a graph in a linear configuration to determine lots of stuff. So if it's a zero order equation, as we've talked about already, you can re-express it in this linear form. And if you graph that, because look, this is y equals mx plus b, right? There's your y, there's your constant slope, there's x that's changing time, and plus b, so the y-intercept over here, right, is actually the original concentration, and that makes sense as the reaction runs on, that the original concentration is the time 0. Okay? Well, look at all the stuff. The slope of this equation is actually the minus the constant. So if you put this together and graphically saw the slope, you could pick all this apart. But the key on this is it's a plot of the concentration versus time. It'll be linear if it's zero order. All right? So now let's go to a first order reaction. And remember, here's the equation. What if we were to rearrange this as it stands into a straight line form? So now, without doing a lot of the math here, but just simply, I got AT, and if I was to divide through, I'd have AT over A0. If I raised both sides to the logs, then I basically would have the log of AT minus the log of A0. And so when I bring that back over to the other side, right, I would basically be B plus, and if I raise this e to the minus KT times a log, that minus KT should come down, and that's what happened here. So you can review your log video and see some of these algebra moves that we've done here to rearrange this into a straight line form, y equals mx plus b. So now if you were to graph this, but you don't graph the concentration versus time, you graph the log of concentration versus time, but you get a straight line. And the slope in this case is not the k, it's the minus k, and the y-intercept here is not the a0, it's the log of a0. But still, this is very useful, all the pieces you could pull out of here. Now we're doing the log of concentration versus time, first order reaction. So we're just going to work up through a second order reaction. Okay, here's the integrated rate law we used the last time. Do a little bit of rearranging. And once again, I'm not going to do the full derivative, but one of the first math moves you might consider is inverting both sides of this expression and multiplying through by a0. But once you do this and collect terms, etc., you're going to end up with this expression, which once again, there's your y, there's your m, x plus, and here's b. When you graph that, now the slope is not a minus k, but it directly is k. The y-intercept, once again, is not a0, but 1 over a0. And what you graph is basically 1 over concentration versus time. So now what can you do with this? Okay, how can you use this graphical analysis? Let's just say I have a decomposition. I basically have N2O5. I can measure this with the spectrophotometer. I can run time along the axis. So basically when I'm done, I get data that says at each time I now have the concentration of the N2O5. So now how can I interpret this based on the graphs we just worked out? Well, the trick is, instead of guessing which one it is, graph it for all three situations. Remember, zero order, time versus concentration. First order, time versus the log of concentration. So all you have to do this on an Excel sheet and take the log of this column and you'll have that. And then remember, second order would be time versus 1 over the concentration. And then graph all three of these. So if I look at the three graphs, it's not zero order, not second order. Oh, but there's that linear relationship. So this is indeed first order. So that's a way to crack the code a little bit. If it's a simple equation, you're down to one thing, basically, although you can... so now we know it's first order. So what can we say about this? All right, now we can start tearing this apart. We can say, okay, we know the general rate expression has to look like this. But can we find the k is the next question. Well, remember when you graph a first order equation, isn't the slope the minus k? All right, so how do you find slope on a linear equation? Divide y minus y over x minus x, and we're going to work on the 50 and 60 minute marks. So we go 5.84 minus 5.55. Notice I don't change the sign at all, and I subtract them. And then I do the correlating x value, which is 60 minus 50, and I get minus 0.029. So now I have the rate constant. And because it's first order, right, this is going to be per, and in this case, it's not actually per second, it's actually per minute. It's 0.029 per minute, and I base that on the time I used over here. Okay? So other physical events that use the integrated rate law. In other words, this is not exclusive, it is chemistry, everything I'm about to show you, but it's things we come to a little differently. But here's something we use in radiochemistry, something we'll study later, and I'll have on later YouTube videos. But if you take cobalt-60 and it undergoes a beta decay, which basically means a neutron splits in half and electrons ejected, is what we call a beta particle. Okay, but the mass number, the number of protons and neutrons, remains the same. But the protons gains one, so you end up with a nickel particle. Okay, so the point is this cobalt is going away. It's decaying, and that's important because these particular particles are dangerous. These are radioactive particles that get thrown out of the nucleus of the cobalt-60. Okay, and sometimes we use them as radioactive tracers or for different things, because there's also energy involved. That's something that I don't have in this reaction. But now, how do we correlate that with what we've just been talking about? Well, radioactive decay is usually a first order event. Now look how this is very similar to a first order rate equation. It is. The decay rate, the amount of atoms that go away per unit time, is equal to some decay constant times the original amount of starting atoms. And as the atoms go away, then the decay rate, the amount of atoms that goes away per unit time, starts to decrease. All right, so now if I was given a decay rate for this radioactive reaction like 4.1 times e to the minus 9 per second, okay, I could actually do some work on this and say, okay, what if I had 0.5 grams of cobalt-60? That's a starting material, right? But that's grams of cobalt-60. I'm needing atoms. So once again, we've got to go back to our stoichiometry and do the conversion. Grams times 1 mole per 60 grams. That is, off the periodic table, that's the molecular weight of cobalt-60, or molar mass. Times Avogadro's number, that's how many atoms are in a mole. A mole is how many. Do all our cancellations here, and we end up with the 5.02 times 10 to the 21 atoms. So now I can just plug that into this expression. I know the number of atoms, I know the rate constant, and if I multiply those together, I'm going to have a decay rate that basically, right from the start, you got 2.1 e to the 13 atoms per second. But once again, we know this is a first order decay rate, so if you want, you could graph this, and you could even use the tricks we showed you earlier too, where you integrate it and graph it, and integrate it and graph it in a linear form. All those things can be applied, and you'll actually know how many atoms are remaining after a certain amount of time. So something that you hear a lot about is half-life, and half-life applies to biology, chemistry, and radiochemistry and physics. And basically it always means the same thing. It means the time it takes for a sample to decay or react until 1/2 of that sample remains. So in this particular radiochemistry example, we're decaying cobalt-60, and we know its decay rate, and we know its decay constant, and we know it's a first order equation. Can you figure out its half-life? How long would it take until it goes to half of that mass or moles of cobalt-60 remains? So let's walk through this proof real quick. Let's go back to the straight line form of the integrated equation, and let's think about 1/2. Okay, here's the starting material, no matter what it is. If this is A0 is 5 molar or 5 moles, then when you're at half-life, then AT is going to be 2.5 molar. Does that make sense? You're down to half of the amount. So with that idea in mind, we can do a little mathematical rearrangement. Okay, negative sign, we'll bring it to the other side, bring this under, and then divide through by log of AT. So now we're looking at this expression, which you can simplify down and distribute that log across both terms there, basically. But now look at this expression. We just talked about this. If you're starting at some concentration, when you've gone to half-life, this is half of that. So basically this expression, 2x over x, gives you the number 2. So KET equals the log of 2. So now we're getting real close. We now have an expression that could solve for t by dividing through by k. And there you go. When you're talking about to half-life, t in a first order equation equals log of 2 per k. All right? And you can also solve for the log of 2, which actually is the decimal 0.693 divided by k. So anything that decays by a first order equation will get to half of its amount or half of its quantity by 0.693 divided by k. That'll tell you until half of it's remaining. So that's a half-life. So this has other applications. Sometimes you talk about an enzyme half-life or a catalyst half-life, which basically means as you use enzymes over and over, they eventually start to die and they're no longer usable. But sometimes when you talk about an enzyme half-life, you're actually talking about how long until it has half of its remaining or half of it's been used up. That's one application. Probably a more prolific application of that is when something's acting on, say, like a drug or something in a biological regime. You're thinking about that, how long it takes for that drug to be expelled from the body. So if you took a drug, how long is that drug concentration active until half of it's remaining, or it shows half activity? So we call that also a half-life. And once again, these often follow first order kinetics. And as you go on in your science and math education, you'll probably learn which are first order, which are pseudo first order, and different things like that. But just for some examples, here's some different drugs. So here's norepinephrine, and that has a biological half-life of 2 minutes. So what does that mean? That means that of the amount administered, half of it will be gone from the body after 2 minutes. And all of these things apply, the rate laws, the half-lives, all that applies to first order kinetics. You should actually take this equation sheet and print it out and spend time memorizing it. And here's why, because with this, if you know it's a zero order equation, you can solve for AT at any time knowing the K and the original concentration. Here's the expression that will tell you the half-life, how long it takes to get to half of its concentration. Here's what the integrated graph looks like, but make sure you pay attention to what you're graphing, time versus concentration here. What else can you find? Okay, you can find the minus k, you can find the A0. Now here's the first order equation. Here's the integrated rate law, which will tell you the concentration at any time. Here's the expression for the half-life, either log of 2 over k, or you can go ahead and solve that and use 0.693 over k. Either one works. Understand that it's linear when you graph time versus log of concentration. And then here's a second order equation. And notice here's the expression that will allow you to solve for concentration at any time. And once again, here's the half-life expression. And finally, in order to get it into a linear form, you graph time over 1 over concentration. So I hope this video has helped you understand kinetics. This was video 3, and I believe it's going to be a 4-part series, and you can find my other videos on YouTube.